Hey friends, welcome back. Today we are continuing our chemistry journey, focusing on what makes atoms masters of pulling electrons. We are not talking magic here, we are talking science. So, specifically, we are zooming into how the size of an atom affects its electronegativity. If it is a big atom or a small atom, does this have an effect of its electronegativity and ability to attract the electrons of a bond? So grab a seat and let's get started. After understanding the nuclear charge in the last step, our next stop is the atomic size. Here is the scoop. The smaller atoms snuggle their electrons closer to their nucleus. Cozy, right? But it also means that they hold on to their electrons tighter. So this means that this increases its electronegativity and ability to attract the electrons. It's like having a strong magnet in a tiny package. So it works better. But how do we know which atom is smaller size or bigger size? That's simple actually, because the lower an atom is on the periodic table, the more energy shells it has. So this means bigger. Let's compare the hydrogen to the lithium, to the sodium, to the potassium. The hydrogen here comes with only one layer, but the lithium has two, and the sodium has three, and the potassium has four. This is the potassium. It has four energy layers. More shells equals a bigger atom with a larger radius. But remember, bigger isn't always better in the electronegativity game. Let's put this into perspective with a little comparison. Take lithium and potassium. Potassium is like the gentle giant here. It's bigger and further from the nucleus. So potassium has one layer, two layers, three layers, and four layers. These layers makes the size bigger. The electron is farther from the nucleus. Its electrons are not held as tightly, making the lithium the stronger one when it comes to pulling the electrons. So lithium has only two layers. Which one do you think will be able to attract the electrons easier? The electron here that's only on the second shell away from the nucleus, or the electron here that's very far from the nucleus? So moving on, we can say that it's more difficult for the nucleus to attract electrons as the distance between it and the electrons will be more. The smaller the atom, the electron now will be what? Is more attracted to the nucleus, increasing the atom's electronegativity. So let's review the nuclear charge and the atomic size. Already we know now about the nuclear charge, and we know today about the atomic size. So more inner shells means electrons feels less of the nucleus pulls. It's as if the nucleus voice gets lost in a crowd. The result, atoms with more shells tend to have lower electronegativity because their nuclear magnet isn't felt as strongly on the outer electrons. Pick the right magnet. Which atom would have a stronger pull on electrons, considering nuclear charge? Is it the atom with 3 protons or the atom with 11 protons? True or false? The larger the atom, so the larger the atom, the closer the electrons are to the nucleus and the higher electronegativity. Is this correct or false? The power of attraction. An atom with higher nuclear charge, so more protons and smaller atomic size will have a lower or higher electronegativity. Please give me your answers in the comments. The answers will be in the file here. Now let's see the third factor. Think of an atom like a house with many floors. So this is my building or my house, and I have many floors here. The nucleus is at the basement, and the valency electrons are up in the attic. This is the valency electrons. If you have more floors or shells, the less the attic hears from the basement. It will be very far, not only very far, as very far means our previous factor, but what's new here? There is some electrons here called the core electrons. So the valency electrons are the electrons which are only in the outermost shell. We don't need to express this term in the exam, core electrons, as is not in our syllabus. Just to know that the electrons in between the valency electron and the nucleus are called core electrons. So the core electrons, let's say we have 2 electrons here, we have 8 electrons here, and we have 8 more electrons here. Let's say we have 8 or 18 electrons here. So can you see? It's like this is our singer, and I'm trying to reach out, but the crowd prevents me. It becomes very difficult for the nucleus to attract the electrons. It's being shielded. The electrons are shielded from the nucleus by all these core electrons. So just like the knights have armors, electron shells can shield the nucleus. The inner shells of atoms act like a shield, blocking the pull from the nucleus, and the valency electrons cannot be attracted well. This is called the shielding effect. So because of this inner shield, the outermost electrons don't feel the full charge of the nucleus. So please remember that the nuclear charge effect is still there. They are still attracting the electrons, but not as strongly. Why is that? Something is blocking their way. The more inner shells there are, the weaker the pull from the center. This means that atoms with more shells have lower electronegativity. So the shielding effect explains why atoms are in the bottom of the periodic table. So here I have the periodic table, and I have atoms here like cesium and francium and rubidium. You would imagine that these elements have higher nuclear charge. So we know that higher nuclear charge means higher attraction between the nucleus and the electron. Yes, there is very big number of protons here attracting the electrons, but there are a lot of layers here in between containing electrons. These electrons act as a shield which decrease the effect of the nuclear charge in pulling the electrons. So the attraction is much less and the electronegativity becomes less. So it's like a sequential flow. The protons in the nucleus attract the electrons. So this is the nucleus, and these are the electrons. So they are attracted by the protons. But the inner shells provide a shield. So the valency electrons feels a weaker pull. In the next video, we'll see the trends in the electronegativity across a period. So how I can compare lithium, which is on the left side, with fluorine, which is on the right side, and how I can compare beryllium, which is at the top, with radium or barium, which is at the bottom. This is called the trends in the electronegativity, and we'll see it in the next video. So see you then.